NetMaster using SmartTrace to diagnose real-world network issues. My name is Anna Clayton, and with my colleague Phil Shane, we will be going through this feature of NetMaster with you today.
Yeah, happy to have you here.
So before we get started, just wanted to take a minute to give a shout out to the NetMaster product and the team behind it. NetMaster turned 40 years old over the summer. NetMaster was first sold to a customer in June of 1983 and has since grown to a huge code base, including 90 applications with over 2,500 scripts, 2,900 assembler programs, and 23 C programs, linked to over 500 load modules. I don't know the number of lines of codes offhand, but NetMaster has grown quite a bit over the last 40 years. In addition, the NetMaster team has delivered on over 100 community ideas. These are suggestions and feature requests for the product that come straight from the customer base. This averages to about 2.5 community ideas per year over the last 40 years that are done in addition to our scheduled updates, improvements, and new features. So thanks to you, our customers, for helping us to create NetMaster over the past 4 decades. Now back to our topic, SmartTrace. Hopefully most of you have used SmartTrace, so a lot of this is already familiar. SmartTrace is our industry-leading packet capture tool that allows you to quickly and easily target and capture the exact data you need to debug, diagnose, and investigate how your network is operating. NetMaster's granular control allows you to target the data and headers of just the packets that you need to see. This helps to cut down on the deluge of data that can result from unbridled packet capture tools. Networks can be noisy, so if you can focus on just what you need, you can do your job quicker. SmartTrace allows you to limit packet capture to headers only capture packets with specific flags or other attributes, truncate packets to only the relevant sections, capture only inbound traffic, only outbound traffic, only traffic to or from a particular network or from a particular port. SmartTrace also allows you to stop tracing automatically using a variety of criteria. You can stop after a specific number of packets has been captured, after a specific flag is traced, or based on the data within the packet. For example, stop when an SSL handshake failure is encountered. After you've gathered a collection of packets using SmartTrace, you can export them to the format of your choice. You can export the packets to CTrace, for example, if you need to engage IBM support. You can export to live PCAP and use tools such as Wireshark to dig down and analyze your data. Or you can view the packet data directly in NetMaster.
When we talk about how do we use SmartTrace, right, we have a variety of options. We have our web portal application. This is our new web application that we have hosted. It provides a really intuitive and easy to understand way to look at SmartTrace, create traces, edit traces, view individual packets, and you can apply various filters and sorts on them. So it's a very useful tool when you're trying to look at smart traces. Next, we have our API, right? This is our REST API. This is actually what's serving data to the web portal, but you can use it standalone, of course. So this is just your typical REST API, and we expose a whole lot of SmartTrace data in there for you to use, right? And then we have the old tried and true method of just the 3270 panels that we have in the base product. Certainly a lot of feature-rich parts of SmartTrace there that you can use. And then we have the exporting feature, right? So we can, similar to what Anna mentioned just a bit ago, we can export your traces to another format for you to use and open up in whatever analysis tools you have locally. So that's just a number of ways we can utilize SmartTrace here. So like I mentioned, we have our web portal. I just wanted to highlight here a couple screenshots that we have from the web portal. On the left there, you can see this is an example of looking at a trace definition for a TCP trace. We can see the various filter criteria that we have set up that we're trying to capture there. And then on the right side, we have another screen cap. This time we're looking at an active trace and we're looking at the packet list. So this would be the list of the packets that are in the trace, right? And then we can see some important information here in the header just to provide at-a-glance information for your SmartTrace, right? And then we also have, it's not highlighted in these images, right? But in the context menu, we can also download a trace, so you don't have to worry about FTPing files off of the mainframe or things like that. If you're using our web application, you can just hit the little download button. It'll download it to your local client for you to open up in Wireshark or whatever third-party tool you have. Next, we have a bit more of our web portal, right? So this is highlighting detailed packet information, right? So this is the actual raw information in the packet. We do provide the raw information on the right side there, as well as the formatted information on the left. So if you want to look at just the pure data, you can do that, but we also have it nicely formatted there for you. And we have a little navigation tool at the top there that just helps us go forward and navigate through the trace, because sometimes there can be a lot of packets in these traces, so we might want to jump around quite a bit. If we go to the next slide, we have our APIs, right? So I mentioned our APIs a bit earlier, but this is just an example of all of these SmartTrace endpoints that we have, right? So you can see various ones in here to get specific traces, delete specific traces, start, stop, things like that. And I'd like to highlight that we are Zoe conformant. We're Zoe v2 conformant. Our REST API works hand in hand with the mediation layer if you want to set it up that way as well. So we provide a lot of options for you and a lot of extensibility with our APIs. Then we have our classic 3270 interface, right? Again, just a different way to look at all of our SmartTrace data. Here we can see looking at the definition list, the packet list, and then the detailed packet display here, right? So just wanted to highlight the various methods that you can use SmartTrace, right? We have a lot of options for you to use. So when we talk about SmartTrace use cases, right, there's a number of places where you can use SmartTrace where it's a really valuable tool and that we use on our day-to-day of network management, right? Some of the use cases that we wanted to highlight in this presentation would be inbound issues, so connections when they're being established. If you're having issues there, you can use SmartTrace to debug them. Similarly, we also have outbound connection issues that we can diagnose with SmartTrace. And then we have performance issues. So this would be like general performance issues, whether it's slowdowns or reliability, things like that. And then naturally, we also have security issues. SmartTrace is a great way to debug various attributes on our network security, right?
And as we chat about these use cases, please keep in mind recent activities and traces that you think would be interesting, how SmartTrace could have been used to assist you, and we discuss these in our Q&A session that will follow our presentation. So inbound connection problems. Say you've had a ticket opened by a client who's unable to connect to service XYZ on your mainframe. They provide their IP address as well as the IP address and port they're attempting to connect to. It takes just a minute to set up a SmartTrace to capture packets exchanged from their IP address to the address and port they're trying. So you do so and ask them to try again. Configuring and customizing a SmartTrace definition is easy and intuitive using NetMaster's panel-driven 3270 application. All of the same functionality is now available on our web portal interface too, so you can use the 3270 panels or the web portal interchangeably. Create the trace definition on either, and view or update it wherever is the most convenient. Values entered in fields are validated as they're entered. This validation saves you confusion and headache stemming from misentered information, misunderstood instruction, omission of data, and a whole host of other simple to make but difficult to debug errors. For example, if you enter an unrecognized TCP/IP stack value, NetMaster will flag it as an error and force you to modify it. If you enter a value that's out of range, we tell you what the allowed values are and flag it on the screen. No cryptic error messages to decode, no searching through every input area on the screen to try and spot the one that's incorrect. When you're done setting up the SmartTrace definition in the 3270 panels, you file it by pressing F3. You're prompted to save it by re-entering F3 or to save and also activate or start by entering F6. You could also decide you're not done editing and simply hit the Enter key to continue customizing the definition. The web portal interface is just as intuitive with drop-down options, data entry fields, and on-screen hints about required fields. Buttons at the bottom of the trace definition screen allow you to save or save and start your trace definition. So back to our use case. Whichever interface you chose to create your trace definition, you activate the trace and instruct the client to reattempt their connection. And your SmartTrace shows nothing. In the screen capture below, you can see that your trace has collected 0 packets. This is indicative of an inbound connection problem. The server is, for some reason, not receiving any packets. Consider the analogy of the photo with the bus. There's nothing wrong with the bus, nothing wrong with the passengers, nothing wrong with the station, but the fact is that the bus is not going to arrive at the station, and that means there's something wrong. In this case, a pretty big problem with the roadway. This narrows the scope of your investigation into your client's issue. maybe a misconfigured firewall, a faulty or unplugged cable, or a missing router. Consider modifying the trace to omit the remote IP address to see if you're getting any traffic on your local port and investigate the traffic. In this case, SmartTrace doesn't give you an exact answer to your problem, but it gives you a good starting point. So just a note on modifying the trace. Modifying an existing SmartTrace definition is simple and intuitive. You can even modify it while it's still running. Put a U to the left of the definition name and hit enter. You're presented with the same set of panels you interacted with to create the trace, where you can modify and remove any values and use F3 to be prompted to save and/or activate the modified definition. The web portal allows these same actions.
Yeah, so now we're going to talk a bit about an outbound connection problem, right? So contrary to the other example, now we are getting inbound connections, and the problem is outbound, like going out of our network, right? So here, this time we do generate packets, which is great news because now we have something to sort of go off of. We have some concrete evidence here to look at and sort of debug what might potentially be going wrong here, right? Say, for example, that we have a user in our network trying to access some application, right? And they're making requests to some server, but they're getting no responses, right? So we can set up a SmartTrace, try and debug that information. We could set up those various filters that Anna mentioned about, and we can look at our packets here, right? So in this case, what we can see is we're getting some inbound packets, but on the outbound, we're resetting the connection, right? So this lets us know that we definitely have an outbound connection problem, and we can sort of debug from here and figure out what might potentially be going wrong. So in this case, what it was just, the application wasn't available. We had to go start the application and then, try and access it again. And we got some good packets back and forth. So it's just a quick example of when you might see an outbound connection problem, right? And being able to determine if our issues are inbound or outbound is a key step in diagnosing our network, right? It always helps out to narrow down and try and be more specific about what sort of problems we're debugging here. And determining inbound versus outbound connection problems is definitely a key step there. So next we're going to talk a bit about network performance issues, right? I have it broken down into a couple different sections here. So firstly, we're going to talk about general network performance issues. Then we're going to do a bit of a deep dive on fragmentation. And then we're going to talk a bit about FTP issues, problems we might have related to them. So the first issue we're going to tackle is just like general network problems. The most common problem with networks is, thankfully not that they're down and we can't access anything, right? That'd be a bad scenario. But mostly network issues that we come across are either the network is running slow or it's sort of unreliable. It's like intermittently accessible and not accessible. So the way we can sort of tackle more general issues like this is, of course, with SmartTrace. And in SmartTrace, we have a type of trace that you can set up that's just called a general trace. And it's used to debug situations exactly like this, where we might not have a whole lot of information to go off of in terms of, where the problem is or what the problem might be, right? We can set up a general trace. And what this general trace is going to do is going to trace all the traffic within our network, right? It doesn't matter what protocol it is, where it's coming from, where it's going to. We're just going to capture all of the information in there. In that way, we can get a bigger picture about our network and where there might be problems, right? You can see in the screen capture right here, just an example where we can see that we have some TCP data, some UDP data, some ESP data, and then as well, we have some SNA traffic as well, right? So it's just a good way to view in general where there might be some problems. Some things you might be looking for on a general trace, right? It'd be the delta between packets, so that time column. It'll show us, if there's a big gap between, an inbound and outbound packet, we can look at that connection and figure out, hey, maybe our problem is coming from here, right? We can also look at the number of bytes in each packet, right? If we have some really large packets, they might potentially be slowing down the network, right? So again, this is just to get a bigger idea, capture more packets, figure out where the problem is in our network. Again, it's always best to set up some filters and try and section off the network into an area we might think we have a problem. But again, general traces are a great way to capture a lot of information and sort of as a beginning point to our debugging, right? So I mentioned a little bit that these big packets might be causing us problems, right? And one reason that might be causing us problems is because of fragmentation, right? So now we'll talk a bit about fragmentation. So fragmentation is when packets are too big for our network to handle, right? What we mean by that is, each given protocol or, potentially hardware limitations, we can't make packets, as big as we want, right? There are some limitations. For example, Ethernet, I think, has 1,500 bytes is the maximum packet size for that. So we can't exceed that. But if we do, what we have to do is we have to break these packets down into smaller pieces, right? So we take one packet that has, 5,000 bytes of data, and then we have to section it off into 1,500 block increments, right? So that process of breaking down those packets is expensive in terms of resources, right? Especially if we have a lot of traffic going through our network. Breaking down those packets just introduces overhead that we'd rather not have to deal with, right? In addition, it's also sort of inefficiently transferring data through our network because, while we break down these packets into smaller pieces, right, there's still the header information in all of the packets that we have to deal with, and that's just duplicated data, right? We're really only transmitting the same amount of useful data, but now we're duplicating all of these header informations, which increases congestion within our network and can make it a bit harder to sort of see what's going on here, right? And then, of course, at the destination, these packets have to be reassembled. The receiving end, whatever application is on that end, needs to reassemble these packets to sort of get an idea of what this connection was actually trying to do. And that process of reassembling the packets again is expensive in terms of efficiency, right? We'd like to minimize this as much as possible. And again, especially if we have a lot of traffic and a lot of packets that need fragmentation within our network, that could create a lot of problems. And we'd like to avoid that as possible. So you might think it would be difficult to find these fragmented packets and sort of figure out where they are, what connections they are getting fragmented. But with SmartTrace, it's actually very easy, right? We just have a specific filter that you can specify, fragmentation, yes or no. And if you have that enabled, you will capture packets that have fragmentation in them, and we can investigate them further and see where they're coming from, where they're going to debug the applications that are having those problems, right? We're not going to go into anything about how to solve packet fragmentation. That's a bit outside of the scope of this presentation, but as far as identifying fragmentation and figuring out where it happens, SmartTrace is a very useful tool for that, right? So next, we can see here I have a screenshot of Wireshark, right? Anna mentioned earlier that we can export our traces to a third-party tool, whatever it may be, any tool that can take libpcap formats, and we can export it there and we can view the traces there, right? So I just wanted to highlight that feature and that functionality in here. Of course, all of this information is available in our 3270, our API, our web application, but we're looking at a packet trace in Wireshark here just to highlight that feature. So what we can see here is we have a fragmented packet, right? If we drill down into these individual packets, we can see some information. We can see that they were 2 IPv4 fragments that had to be created from this connection we're dealing with here. So if we look at these various packets, we can look at the flags, how big they are, things like that to sort of debug why we might be getting fragmentation, right? So the next topic we're going to discuss a bit about is FTP issues, right? SmartTrace, again, is a great tool for debugging any FTP issues you might be having. Typically, when we see FTP issues, often that'll be when we're either establishing the connection, right? When we're trying to establish between the FTP client and the FTP server. That is a part of the process that is prone to errors, right? And we could, of course, use SmartTrace to debug that. And then similarly, we also have timeouts that can be a bit problemsome when we're dealing with FTP, especially if we're FTPing large amounts of data, right? Oftentimes well, hopefully not often, but sometimes timeouts do occur, and we have to sort of debug them and figure out why that might be happening, right? Again, SmartTrace is a great tool to do that. What we can see here is we set up a SmartTrace between our FTP client and server. We started the FTP, started capturing packets, and we can see that packet data here. We can see in this case that we were retrieving this netmaster jar file, and then all of a sudden we stopped transferring FTP data, and we saw, highlighted in red there is our reset packet, right? So the connection abruptly ended. And then in the next line, we see that the transfer was aborted, right? We can see our FTP status code, right? And that's something you would get back in your client, but by using SmartTrace and looking at packet traces, we can get a whole lot more information as far as why we got that error. It's not just some cryptic error that we have to go look up. Here we can look at packets. and see the exact flow of what happened and what went wrong, right? So it just provides us a bit more. And of course, we could also look at the flags, look at the sequences, window sizes, things like that are available here as well, and that might be causing us issues. So SmartTrace just provides us a lot of additional information. So there's another part of SmartTrace definitions that I would like to highlight and I think is really useful for FTP specifically, and that would be the packet data section of a SmartTrace definition. So what this sort of menu allows you to do is look at specific packet data within the packet, right? So we're not looking at header information, we're looking at the actual data within the packet, right? And we can set up conditions to where we will only trace packets that meet our various criteria, right? I think it's best, explained with an example here. In this first screenshot, we're taking a look at error codes, right? So I mentioned a little bit ago that FTP, much like a protocol like HTTP, has error codes, right? I'm sure you've all seen an HTTP 404 error code indicating that the resource isn't there. FTP has something very similar, and we can sort of exploit that and use SmartTrace to capture packets that only have FTP errors in them, right? That way, we can sort of proactively monitor our network, and we don't have to worry about recreating a difficult issue. If we have an FTP failure, we'll immediately have the packets captured for that failure, and we can just immediately start debugging them and figure out what went wrong, right? We don't have to mess around recreating issues. And the way this sort of works here, right, is we can set up expressions. So in this first expression, we can see we're using the equal operator, and then we're looking specifically at the number 4 in an EBCDIC format at the first position within our packet data, right? We're also looking at the second line here. We can see it starts at the 5 at the first position, and then we have a 40 in hex, which just translates to a space, right? I mentioned that FTP is a well-defined protocol, so we can sort of use that to our advantage here. And in this expression statement we have here, we can see either 1 or 2 and 3, right? So what that's basically saying is if the first expression matches any packet data, or the second expression matches any packet data, and the third expression matches our packet data, then we'll immediately start capturing those packets. And the way this is used, right, is that any FTP error is either going to start with a 4 or a 5 in the first position, right? So if we come across a packet that has a 4 in the first position or a 5 in the first position, and then followed up by a space at the 4th position, right, we'll immediately capture those packets and we'll have those FTP errors ready to go and ready to trace, or ready to debug and sort of figure out what went wrong. We can do something similar looking at specific data sets. Say you just released some internal tool that you think a lot of people are going to be accessing, and you want to make sure that it's available. And if people have problems, you want to be notified of that so you can debug them. Or for, say, example, you're auditing a specific file, you want to keep track of what users access a specific file. We can, again, use SmartTrace and this packet data information to get that information and create those traces in those packets, right? So with this example, we're going to be looking in our network for any packets that start with the retrieve function, right? That retrieve is an FTP method that we can use to get a specific resource on a server, right? So we're doing a retrieve of any public data set, right? So we're specifying this high-level qualifier here. It's a public.star. That's what that like operator allows us to do. It allows us to create captures of more generic things, right? So what this is doing is it'll monitor in the background any packet data that has a retrieve of this public data set. We're going to start tracing that packet data there. Again, this is just 2 examples of what you can do with this packet data section. There's a whole lot that you can do here. This is a really advanced functionality that we provide. You can get very specific with what you're trying to find in your packet data. So it can really help debug very specific problems that you're having, or generic ones too. It's a very powerful tool we have here. So next, we're going to talk a bit about security protocol issues, right? So SmartTrace, again, of course, can be used to debug security issues in your network, right? And we're going to look at some ATTLS problems, some handshake failures, and then specifically problems with certificates as well. When it comes to security and SmartTrace, there's a whole lot of information and a whole lot we can do with it. I think it's best to sort of walk through an example, though. sort of bring it back to the real world, sort of debug your problem start to end using SmartTrace, right? And this is going to be a security related problem, right? So this example I'll walk you through is an actual issue we had with a user of NetMaster, a customer of ours. And of course, we're not displaying any information here. We've recreated it in our own environment, but it's just as an example problem to walk through, right? So just a bit of background about the issue that we're dealing with here. We're making two requests to an API, right? So everything is the same between the two requests. However, the problem we're having is that the first request works just fine, but the second one doesn't, it fails. And we need to sort of figure out what could be going wrong and sort of why that's happening, right? So naturally, the first thing we're going to do is we're going to set up a packet trace. In this case, I know the exact hosts we're working with here. I'll specify those here so I can capture packets only specifically for those connections I'm dealing with. I know exactly where the client and the server is in this example, right? So what we're going to do is we're going to start the SmartTrace, make our two requests, and then we can start debugging the packets and the traces that we have from there. So here we can see our two requests, right? The first one on top is the good request, and the second one on the bottom, as exemplified by all of the red packets here, that's definitely our problem trace, right? So I've sort of trimmed the traces here to look at just the specific information that can help us debug the problem, right? Obviously, we'll have more packets in the full trace, but just for the presentation's sake, it's a bit easier to look at the packets in this view, right? Again, we're using Wireshark. Of course, you can use NetMaster 3270, the web portal, or the API to debug this. I think it's a bit easier to read for a presentation in this format. So here we can look at the two requests, right? We're starting with the client hello, right? This is the handshake, the TLS handshake in progress. This is where it's happening. And we can see that it all looks fine. Everything between the two requests looks good. We see them change ciphers. That's fine. That's, acceptable. And then the good connection starts transferring application data. But we can see here the bad one, we get an alert that says, level fatal, description, bad record MAC, right? And then we can see that the connection resets and then it completes, right? We get that fin and the connection closes, right? So automatically, this is just a bit more information that we would have gotten from our server and our requests, right? We would have typically just seen an HTTP status code, probably a 500, indicating that the request was bad. But here with SmartTrace, we automatically have some more information, and we can see that this is a bad record MAC, right? So we have some information to go off of now in terms of, what's going on here, what the problem is, right? So naturally, the first thing I'm going to do is I'm going to Google it, right? I'm going to say, hey, what is a bad record MAC? What are some examples where this might happen? Why might I be getting this error? So I find some online resources. The first one I come across here is a handy dandy Stack Overflow message or post that says, here's what a bad record MAC is and why you might be getting one, right? I'm not going to expect you to read this right now, but I'll summarize quickly and just say, when we're dealing with a client and a server, we have to establish the connection, and we want to make sure we're using a secure connection. And so both the client and the server have to agree on what sort of cryptographic elements they want to use, whether it's a protocol, ciphers, certificates, public keys, private keys, right? Both ends of the connection need to agree on what cryptographic elements we're working with here, or else they're not going to be able to establish a secure connection. So basically, all of that is summarized into a message authentication code, or a MAC, right? And if those two MACs don't agree with each other on the client and the server, we'll get a bad record MAC, thus having a failed request. So that's sort of why we might get this bad record MAC, right? So now that we know a little bit about the problem and where we might be having the issue, we're going to start our presentation on a comprehensive guide to TLS certificates, ciphers, and more. I hope you're ready for an in-depth presentation about these security attributes. Just kidding, of course, we're not actually going to do that. Let's just go and look at the trace. I'll sort of summarize that information here for you. So here we're looking at the trace. I went back and looked at the client hello, right? That's where the security exchange happens. And we can see here we're looking at specific packets, and we're looking at the TLS information on those packets, right? Again, the left side is the good request, the one that's working, and the right side is the bad request, the one that's not working. So we can immediately see here, let's try and find some differences between the two, and that might help us figure out why we might be getting this bad record MAC. There's some cryptographic elements here that are not lining up, right? So we can see automatically here, right? We're using TLS 1.3. That's good. They both agree with that. You can see that this is the handshake in process. We can see version TLS 1.0. We don't have to worry about that right now, but this connection is using TLS 1.3. Next, we can see the length field. So there is a difference here. That might not necessarily mean there's a problem in this section, but it's good to keep a note of. So now we start going into the protocol itself. Now it's into sort of the nitty-gritty information about TLS. Here we can see, again, the length differs slightly. We see the version of TLS corresponds. We see this random attribute. Naturally, that is different because it's inherently random. Then we can see the session ID, same there. And then, cipher suites, that's an example of where these cryptographic elements might not line up. But here we can see that they're both 172 bytes long, and then we can see there's 86 cipher suites in both of them. Again, we could expand these to make sure that the exact suites correspond with each other in both ends of the request, but we can be reasonably sure, since there's 86 in both of them, that they are the same, right? Next, we get to these compression methods. Not a whole lot going on here. Now we get to the extensions. So these are additional bits of information. Think of them as like additional features in TLS that we can sort of take advantage of. That's where you would see in these extensions, things like that. So they all look pretty good, except if we see at the very bottom on the left one, it just ends with this PSK key exchange. But on the right, we see this additional extension that's the pre-shared key, right? So that indicates to me that there's potentially a problem with this pre-shared key. The first request doesn't have that pre-shared key, whereas the second one does. So I immediately think, hey, this is, potentially a problem. What might be wrong here, right? So naturally, I'm going to go look up and figure out what pre-shared keys are, but I'll sort of summarize and say, as a feature of TLS 1.3, right, we can sort of speed up the connection establishing process by, the first connection, or the first time we establish a connection, we're going to exchange all this cryptographic information. We're going to agree on various attributes. And then rather the second request, having to do all of that information again, exchanging everything again, what we can do is just look at this pre-shared key. So this is a key that was generated from the first time the connection happened. And with this pre-shared key, in theory, it speeds up the connection process because now we have something to go off of. We already know that the two sides of the connection agree with each other, right? But in this example, we can see that that's clearly not happening. We're having a problem with this pre-shared key. So we can debug this a little bit more, but I think it's time at a good point to sort of zoom out a little bit and think, okay, how can we fix the problem? Are we at a point where we can fix the problem, right? We can see there's a number of ways we could fix the problem, right? So we think it's probably with pre-shared key, and I know that these pre-shared keys are a feature of TLS 1.3, which we were using. So what I can do is I can go to our ATTLS policy, right? Where on the mainframe, a lot of our connections are secured by ATTLS. I can go and change our policy for this connection to just change it so that we automatically use TLS 1.2 instead of TLS 1.3. So that's an option. Alternatively, we can configure TLS 1.3 to not use these pre-shared keys, and that's certainly an option as well. Or what we can do is sort of debug further and figure out, why these pre-shared keys are causing problems, right? Again, this is a feature of TLS 1.3. We would expect it to work. So there's probably something going on here on why this is happening. In the real world, I think that's the best option that we can take, right? We want to get to the root cause of the issue. But then sometimes we just have to get our network up and running. We have to have our connections working and our servers up, right? So what we decided to do here was change the ATTLS policy to use 1.2 instead of 1.3. We restarted the connection, and then sure enough, that time it worked. We weren't using those pre-shared keys. Ultimately, what the problem was that the Tomcat server that was hosting this API was not configured to use TLS 1.3. So it was getting that pre-shared key, and it didn't really know what to do with it, right? So that was the root cause of our problem. So when we think of SmartTrace and how it helped us here, we were able to very quickly set up a trace for the specific connections we were working with and immediately start capturing packets and sort of debug the problem, figure out what's going on, right? It was a very quick lead time up to that. When we think of alternative approaches, there's a couple that I could think of. One would be using CTrace, right? And that's certainly an option. But with SmartTrace, I think it's a bit easier to get one set up and start debugging the packet information. as well as with our web application, looking at the packets in there or exporting them to Wireshark is quite handy for us. And I think SmartTrace allowed us to do that very quickly and easily. Another alternative might be, combing through the logs for this server, and that's certainly an option, but then we're sort of up to the whim of the server in terms of what it's going to output in the logs. It might not necessarily even give us that information that we were able to get from those packets, right? We got that bad record MAC in the packet, and that's what led us to the solution of our problem. Looking through the server logs, we might not have seen that, right? So I really think SmartTrace is a great way to sort of debug network issues that we're having, just because it's very easy to use. It's accessible in a lot of different places. Again, we have that exporting feature that's really handy. And I think it's a great way to sort of solve our problems, as exemplified by this example we just walked through.
All right, thanks, Phil, for those use cases and those examples. Here's another real-world example of how you can use SmartTrace to help solve a security-related issue. Consider this next scenario. You've had reports from various users having issues establishing connectivity to a resource that is protected by SSL or TLS. These issues are sporadic, unpredictable, and along with the failures, you've also had plenty of users reporting being able to successfully connect. Time to figure out what's going on. You decide to use another feature of Netmaster, the SSL handshake event detector, to confirm that your issue is caused by handshake failures, because when you start the event detector, you get alerts notifying you of these failures. As a side note, Event Detector is another great feature of Netmaster, but it's out of the scope of this session. If you've never used it and want to learn more, let us know in the Q&A session that follows our presentation or by email at any time. So you've got alerts notifying you that handshake failures are occurring. What do you do now? When you view the alert and access Netmaster's help contents related to the alert, you see that the handshake failure can be caused by a variety of things, and that one of the recommended actions is to use SmartTrace to gather more information if and when the failure occurs again. Let's do that. SmartTrace has a lot of built-in features to help you get just the information that you need. First, you can use SmartTrace's multiple TCP connection trace to capture packets from different TCP conversations and segregate them into their own trace instances. You can enter the local and/or remote IP address and port to focus on traffic you know or suspect is encountering errors. You can limit the number of packets that are captured for each connection. You can also limit the max number of connections to trace to avoid a deluge of captured data. A handshake failure would typically happen early in the conversation. If the client and server exchange more than 10 or 15 packets, it's probable that no handshake failure has or is going to occur, and the packets that were captured in the entire conversation can be discarded or ignored. You can have SmartTrace recognize a packet that indicates a handshake failure has occurred and stop capturing packets when this condition is met. And when the condition is seen, you can view, save, and/or export the set of packets and diagnose the error. Here's an example of the parameters used to set up such a trace. On both the panel-driven interface and the web portal, we divide the trace definition criteria into separate sections. You've entered the stack, the local host and port, and the remote host matching the event detector notification to focus only on traffic between these hosts. In the next panel, you've instructed SmartTrace to stop tracing if it encounters a packet with a signature that indicates a handshake failure has occurred. A packet containing a value of 1503 in hex at the first character position in the packet data and a value of 02 in hex at character position 6 is what we're filtering on. That's kind of the snapshot of what a handshake failure looks like. We've included the logic expression 1 and 2, meaning that if both of these attributes are seen in the same packet, we'll stop the trace instance. Finally, you've entered some more trace options. A trace limit of 25 means only save 25 packets per connection, and stop at limit yes means once you've gotten to 25 packets, just stop tracing. That's the case where you've likely got a successful connection and no handshake failure. You're only going to save 100 trace instances or sets of packets to avoid gathering too much data. Yes, there is such a thing. When you've gotten your recreate of your failure, you can stop gathering data. Most importantly, you've told SmartTrace to discard the sets of packets if the trace stops and the stop condition or the special handshake signature packet was not seen. Start this trace definition and keep it running, and when and if a handshake failure occurs between the indicated local and remote host, the packets will be available to diagnose when and why the failure occurred. So in this presentation so far, we've focused on the 3270 panel-driven interface and the web portal to create and interact with SmartTraces and packet data. But there's one more way you can do it, and this one can be automated. You can use Python and our REST API to respond to the handshake failure alert from NetMaster's event detector by creating and starting a customized SmartTrace definition, all via a short, easy-to-read Python script. The one I wrote was fewer than 200 lines of code. To make this work, you'll want to configure the event detector to deliver an email notification if a handshake failure is detected. If you want more information on event detectors, let us know after this session. You can write a Python script that runs in a loop and a block of code to query the email address where these notifications are delivered and recognize when one is received. You can use a code snippet similar to the one shown to parse the local address and port, client address, and stack from the email subject line. So you configure these parameters to create your trace definition in JSON. You can see in this example, we've instructed NetMaster to create a multi-connection trace by including the type key in the parameters and assigning it a value of mult. We've filled in key value pairs for the stack, localhost, remote host, and local port with the values parsed from the email notification. We've defined our stop criteria to match what I showed you in the previous example. Stop if a packet is encountered that meets both criteria, a hex 1503 in byte 1 and a hex 02 starting in byte 6. Finally, we've included some key value pairs to define our trace options. Discard the set of packets if the stop condition is not seen, limit ourselves to 100 trace connections, and limit each trace to no more than 25 packets. Your Python script will use the Python request library to issue a POST request to the NetMaster API server to create the trace and a PUT request to start the trace. Our REST API is publicly available and well documented. Simply call the endpoints, indicating which region name and trace name you'd like to use, and provide a username and password. For the POST request, pass along the JSON parameters you built in your script. Verify that you get the expected response codes from the API server and watch the magic happen. So to recap, you've set up your event detector within NetMaster to alert you by email if a new handshake failure has been detected. Your Python script, which was started prior to the event detector, is periodically polling this email address to react if a notification is received. When an email notification from the event detector is received, the Python script uses the SmartTrace REST API to create and start a customized multi-con TCP connection trace. The end result is a packet trace showing the full packet flow from initiation to failure, including details of all requests and responses. You can view these packets directly from NetMaster, or you can download the packets and use Wireshark or another packet analyzer to diagnose and fix the problem. You can also have your Python script use the REST endpoints to detect that a trace instance has been created and not discarded, and download the trace instance. This is out of the scope of this presentation, but I successfully built this script to prove the concept and would be happy to discuss this with any of you. In conclusion, we've shown you many ways that SmartTrace can aid in diagnosing common network problems and given examples of the parameters you could use to create an effective definition. However, we don't expect you to reinvent the wheel. There are a number of sample trace definitions, many of them doing the same or similar things as the trace examples we showed today, that are provided with the NetMaster product with no special configuration requirements. These samples are available on the 3270 panel you used to create a new SmartTrace and can be used as a starting point and customized as needed when using SmartTrace. Thanks for attending our session today, and we invite you to please share your feedback on today's session. We also invite you to stay in the room and join the live Q&A session immediately following. Thanks, everybody. Bye.